Hello friends, welcome back to my YouTube channel. So in today's video we'll see one more problem of how to solve the problem by using the flexibility method. It is also called as the force method or compatibility method. So this is the given problem. So analyze the continuous beam by force method and determine the member forces. So we need to find the member forces here. So first step is to usually find out in the DS. So here the beam is carrying the UDL throughout the structure. So for that, here for hinge we have the how many reactions? One is vertical, one is horizontal. For roller we have only one, that is vertical. For here also we have only one vertical. So in force method we need to neglect the horizontal. We need to neglect the horizontal reaction or load. So we need to neglect the axial deformation. Axial deformation is nothing but this horizontal reaction. So our total number of reactions becomes here 3. So for that we have the formula E minus R minus EC is nothing but our internal length. There is no internal length, so it also becomes 0. So our total number of reactions are 3. So for static equilibrium equation we have 2. One is summation of Fy is equal to 0 and summation of all the moment is equal to 0. So we don't consider summation of Fx is equal to 0. We need to neglect this axial deformation. So I'm only taking summation of Fy and summation of all the moment is equal to 0. So formula is, sorry, I have written wrong. I will write here. The formula is R minus E minus EC. So EC is 0. So number of reactions are 3. Equilibrium equation is 2. So 3 minus 2, it will become 1. So 1 means the number of redundancies we need to release in this structure. So how many number of redundancies are there? Here one number of redundant is there to make it statically determinate. So the structure is statically indeterminate. To make it statically determinate, we need to remove one redundant from this structure. So I am taking support B. This is the A, this is B, this is B. I am taking support B and considering it as the redundant. So I am giving it name to the coordinate number 1. So coordinate number 1. So we need to release it. So I will show you. See here, I have released the roller support and at B, so redundant number 1 is acting, so I gave it the coordinate number 1. So while calculating I will show you. So this structure is called the M, capital M. This is called the M1. For this diagram there will be two diagram. One is this and one is M1. One is capital M, one is small m. So now we need to find the for two structures reactions we need to find. So here RA takes place, here RB takes place. So this is a single span to find out the reaction. So total load is equal to UDL is there now 30 into at the distance of it is acting 7 meter divided by 2. So it comes 105 kilonewton. So it is nothing but our RA is equal to, this is RC, is equal to 105 kilonewton. Both are going upside, so it means the direction whatever we gave was right. This is also 105. So this is the RC and RA. Similarly we need to find for M1. This also we need to find the reaction RA and RC. So for this moment about C is equal to 0, clockwise we need to take the positive. RC is moving anti-clockwise, so minus RC into a distance of from here to here is 7 meter. So 7 plus, so 1 kilonewton of unit load is acting, so it is positive, it is moving like this, no, clockwise. So it is moving clockwise. 1 into at a distance of from here to here is 4, here to here is 4, and here 3. 1 into 4 is equal to 0. So RC will come out as 0.57 kilonewton. So it is upward. So whatever the direction we gave was correct. Similarly, we need to find the RA. Summation of all the vertical forces is equal to 0. Upward we need to take the positive. Here RA and RC are moving upward. So RA plus RC is equal to 0. RA is equal to, so one more load is coming down, it means minus 1 will come. So RA is equal to 1 plus 1 minus, so RC value, if it comes right side, it becomes minus 1 minus 0.57. So finally it comes 0.43 kilonewton. So RA will 0.43. This is how we need to find the reaction for this diagram. Now we will see the how to fill this unit load table. So by using this diagram we need to fill this here. So our member we got AB and BC, two members. So AB and BC. For AB I am taking the origin as A. For BC I am taking the origin as C. So EI for AB is, EI for AB is 2I and for BC is I. So 2EI, and for this I, limit is, for here 4 meter is there, no, here 3 meter. So for AB 0 to 4, for BC 0 to 3. So 0 to 4 and 0 to 3. So for M1, how to find the M1, we'll see. So for AB this is B, and for AB if we cut the section, x is far away from the origin A. For AB we have taken origin as A. So if we cut the x-axis section, x far away from the origin A at a distance of x, so our M becomes, here one load is acting, RA is acting at the intensity of 105 into at what distance it is acting. So 105 into x, from here to a distance is x. So we need to multiply 105 into x. So I will write here. So it is going upward now. We need to take the positive. So 105 into x. So it is, and similarly here one more unit UDL is acting. So it is of 30 kilonewton per meter. So at what distance it is acting? 30 into x, from here to here is x, 30 into x, and UDL always act at the distance of L divided by 2. L divided by 2 is nothing but our distance is x, so x divided by 2. So 30 into x divided by 2 we need to take. So it is moving anti-clockwise, so we need to take the minus 30 into x divided by 2. So x divided by 2 is, the UDL is always act half of the distance. So minus, it is anti-clockwise, so minus 30 x square divided by 2. So 2 1 ja 2 5. So 105x minus
15x square.
So for M1, if we see, for AB we have taken the origin as A. If we cut the section, x is far away from the origin, A. So unit here 1. RA is acting at the intensity of 0.43. So it is moving clockwise. So for that we need to take the positive 0.43 into at what distance it is acting from here to here is x. So 0.43 into x it is acting. So our m1 will be 0.43 into x. So m1 will be 0.43 into x. Is there any load? So we need to see only this AB portion. We should not see this. Similarly for BC, we have taken the section, we have taken the origin as C. Now we will see for BC, we have taken origin as C. So if you cut the section x-axis far away from the origin C, so it comes here, x-axis at the distance of x. So here RC is acting, so it has the intensity of 105. From here to here at what? So from here to here at what distance it is acting? It is acting at a distance of x. So 105 into x. So it is also going upward. Now we need to take the positive. So 105 into x. So minus here also UDL is acting.
So always remember while calculating the moment above the section we need to take the positive and below the section we need to take the negative. UDL is moving downward, we need to take the negative here.
So here one more load is acting, that is UDL acting. So 30 into at what distance it is acting? It is acting at a distance of x. So 30 into x divided by 2, because the UDL always act at the half of the distance. Half of the distance is nothing but our distance is your x, no? So half means x divided by 2. So 30 into x divided by 2, it becomes 30x square divided by 2. So now we will write 105 into x, 105x minus 30 into x square divided by 2, 2 1 ja, 2 1 ja, 2 5 ja. For similarly m1 for BC, so if I take the origin as C, if you cut the section far away from the origin C at a distance of x, so here RC is acting, so it has the intensity of 0.57. At what distance it is acting? It is acting at the distance of x. So it is going upward, no? For that 0.57 into x. So our m1 becomes 0.57x. Is there any load is acting? No, we need to see only this B to C section. We need to see only this one. So here 1 kilonewton is nothing but our unit moment. We need to apply the 1 kilonewton. So at the support where we have taken the considered as a redundant, we need to at that place we need to apply the unit moment of 1 kilonewton. That's why I have taken 1 kilonewton. So now we have filled all the moments value. So now what we have to do is we need to find the, for this we need to find the flexibility and also displacement. So here we have only two moments now. For that our flexibility will come only one. So that is F is equal to integration of 0 to L m1 square ds divided by ei. And similarly our displacement also comes only one, because we have only moment 2, 0 to L capital M into small m 1 divided by ei into dx. If we have the here m2, then we need to take the f11 f12 f22 f21, like that we need to find. Here we have only moment 2 moment, now we need to find the f and d. So now substitute all the value for AB. So for AB we have the limit 0 to 4. So 0 to 4, m1 for AB is 0.43 x whole square. Here value is 2 into dx plus integration of 0 to for BC is 0 to 3, limit is 0 to 3, and m1 will be 0.57 x whole square. Ai value is 1. So I am not so by using calculus we need to find out it. So I will write this value also, then I will do calculation. For D, integration of for AB we have the limit 0 to 4 m into m1. So m is 105x minus 15x square into dx. 15x square into m1 we need to write into 0.43 x into dx. So here value for AB is 2 divided by 2 plus integration of for BC is limit is 0 to 3 this into this one. So I will write here. So I will write here only. So 105x minus 15x square into 0.57x into dx. Here EI value is 1. So now solve it by using calculus. First I will find the f. So integration of, will solve f. So this one integration of 0 to 4, integration of 0 to 4 into 0.43 x bracket close whole square divided by 2 is there plus this one. Integration of here limit is 0 to 3, here limit is 0 to 4 and for the 0 to 3. So 0 to 3 into 0.57 into x close the bracket whole square. So now solve it. So our f value will come out as 4.89. So it will be 4.89. Similarly for D we need to calculate integration of 0 to 4 into 101, sorry, it is 105 into x minus 15 into x whole square close the bracket into 0.43 into x. So again bracket 0.43 into x close the bracket divided by 2 is there. So divided by whole divided by 2. So plus this one integration of plus integration of 0 to 3 into 105 into x 105 into x minus 15 x square close the bracket again into 0.57x. So 0.57x close the bracket. So now solve it. So our D value will come out as 640.71. So D value will be 640.71. So now from the compatibility equation, so that is P matrix is equal to flexibility matrix inverse of it into dou matrix minus displacement matrix. So your P matrix is nothing but or whatever the redundant we have considered here at point support B, we have released the redundant and consider it as the redundant. So I have taken at support B as the redundant. So P value is nothing but that redundant value. I am taking it as RB. And matrix of flexibility F11 we got was how much? So we got was 4.89. So put it here. So flexibility matrix is nothing but our dou and your D is nothing but our displacement matrix. So I have written here. So I'll put it here. Substitute all the value. The value we got was 4.89. Universe submit. This value becomes 0, not given. Into minus of DL value we got was how much? 640.71. So 640 point minus of 640.71. By using calci we can calculate it. So 4.89 universe into minus 640.71. If we do, RB value will come out as minus 131.02. So RB value is equal to minus 131.02 kilonewton. So this is our given beam. So our RB value is minus, it means it is going downward, 131.02 kilonewton. So now we need to find this is our RB value. We need to find the RA and RB also. We need to find these two. So by using this value we will find out summation of moment about A is equal to 0 clockwise. We need to take the positive. So I will write here. So UDL is acting, so it is moving clockwise. We need to take the positive. So 30 into at a distance of from here to here is 7 into UDL always act at the distance of L by 2. L by 2 is nothing but, or half of the distance. Half of distance is nothing but 7 divided by 2. 7 divided by 2 is nothing but 3.5. 3.5. And plus RB is acting, it is also moving clockwise. We need to take the positive. 131.02 at a distance of from here to here is 4. 131.02 into 4 minus, it is rotating anti-clockwise, so minus RC into at a distance of from here to here is 7. 7 is equal to 0. So now solve it. Our RC value will come out as 179.87 kilonewton. So it is upward. So it means the whatever the direction we have taken, it is right. RC value is 179.87. Similarly, we need to find the RA. For that, summation of all the vertical forces is equal to 0 upward. We need to take the positive. Here RA is going upward, RA minus RB is coming downward, so minus RB, and plus RC is also going upward, positive RC, minus, if you convert UDL into point load, it moves downward like this. It comes like this. Now it moves downward means negative. So minus UDL is 30 at a distance of from here to here. UDL distance is 7. So 30 into 7. If you convert UDL into point load, it moves downward. So now substitute all the value. RA minus RB we got was 131.02 plus RC value is 179.87 minus 2110 is equal to 0. So now solve it. Our RA value will come out as 161.15 kilonewton. It is also going upward. It means whatever the direction we have taken here, right. RA value is 161.15 kilonewton. And now we got all the value RA, RB and RC value. This is how we need to find all the reactions. So by using the static equations, we need to find all the reaction. So RA value we got was 161.15 kilonewtons going upward. RB is minus 131.02 kilonewton. It is also going downward. RC is equal to 179.87 kilonewton. It is also going upward. So here our problem ends. So if you like the video, like it, share it and subscribe for the more videos. Thank you for watching.